This next chapter is, as I keep saying for a lot of things, is a continuation of the previous topic. Now, what we're going to do is we're going to really understand the concept of how electrical flow exists and works. So it's called current. And a lot of you probably heard that term before, current. If you've heard it before, it's probably related to water usually, current, the flow of water. So the current of the river, right, is the flow rate usually. You can think of current of water through a pipe. So some sort of HVAC system, so a heating ventilating system usually runs either air or some sort of a refrigerant fluid through its cycle, and that's a current, that's a fluid that has a current that flows through a circuit. So that's a very mechanical, easy way to interpret the term current. What we're going to look at current with here is electric current. So consider that analogy that I just gave you, that concept of like water flowing through a pipe. That's what we're going to be thinking about here. Instead of water flowing through a pipe, what do you think it is for electric current? Instead of water flowing through a pipe, what would it be for an electric current?
Electricity.
Yeah, good. Electricity in the form of?
Like electrons going through the circuit.
Yeah, good. So she said through a wire, through a circuit. Very good. So electrons flowing through a circuit or through some sort of a wire. Now, just like a pipe's cross-section and parameters affect the flow, so do the wire's parameters. For example, if I had, I don't know, some sort of water system that, for example, it's kind of gross, sorry. Easy one to use though. Your waste pipe at home. So your waste pipe, yeah, I know. It's just the easy example because you're gonna see what I'm saying with parameters. All of your pipes from like your shower, your sink, your toilet, everything that's like water that will not be good water afterward after you use it, goes into their own pipes. Those pipes all merge together into one bigger pipe that leads out to the sewer. That's how it's the truth how it works. The pipe that leads out to the sewer though is like 4 inches in diameter. Because if you think about it, you have like 4 pipes coming together, each with a 1-inch diameter. That bigger pipe, that other pipe that they flow into, if it's not big enough, what'll happen? It'll burst or it'll get clogged, one or the other.
Nice.
Bursting is terrible. It's probably worse. Getting clogged is worse because you experience it firsthand. And this has never happened to most of you, I'm sure, because you probably have really good piping in your system, your house or the house system. But I have definitely been places in the world or places in life where the piping is not that good. And when something gets clogged and the cesspool is not emptied or there's a problem with, like people have what are called cesspools. Anyone know what that is?
It's like a meeting area for water, disgusting water.
Yeah, it's a chamber that holds your waste pretty much. If there's no sewer in the area, and then they empty it and stuff. They have to actually empty it out. But if that gets clogged, a lot of that stuff cannot flow anymore. But if it gets clogged at the actual pipe and bursts underground, then you have to have the sewer company come in and actually fix it like that. So that's actually a much worse problem, even though the first problem, it occurs in your house. The other one occurs like below your house.
You know, it comes up in like your grass and stuff. It's gross.
It comes up everywhere.
You know in the movies where it's like it explodes and it goes everywhere? Is that an example?
It could happen, but that's an extreme example. Yes, but that would be an example. So in this case, sorry, that was really tangent. In this case of electric current, we're going to consider the fact that, well, electrons need to be able to flow through the actual wire. If the wire's diameter is too small, the electrons are going to not move as fast. If the wire's material is different, the electrons aren't going to move as easily. It's called resistivity, or conductivity. The word is actually useful. So here we're going to really study the theory behind electric current, and then we'll apply it in the next few sections. So we're going to look at the properties. We're going to talk about charge carriers and electric fields. So in 17.3 we talked about electric fields. A circuit, when closed, the circuit is currently open in this room, meaning the lights are not on. There's an opening in the wire somewhere. If I close the wire, the electrons can flow. Think about like if you suddenly take a pipe and cut it, the water starts flowing out. It doesn't complete the cycle it wants to. So if I take the wire and literally open the circuit, it means I'm closing the light. And open the circuit. And we'll learn about circuitry in chapter 20, but the idea applies to this. When I close the circuit, what's happening, as soon as I hit the switch, there's a delay for some lights now because of the actual nature of the lights. They're different than old light bulbs used to be. But when I hit the switch and it closes the circuit, an electromagnetic field is established. And we're going to see how that electromagnetic field only takes an instant. And we're going to talk about the speed of it as opposed to the actual charge carriers, the electrons themselves. And then we're going to talk at the end about something called DC and AC. Okay, Okay, different types of current. Different types of current. So let's start first with current and its definition, and we just spent a little while talking about this, so it should make sense. Okay, it's the rate at which electric charges, aka charge carriers. It's an easy way to use a term for that. Some people like to say electrons, but in a moment you're going to see why we don't usually always use the term electrons. The charge carriers themselves, the rate at which they move through a given area. Okay, so it's like an electric flow rate. Just like water has a certain flow rate. Some examples of where this is, obviously, machinery, appliances, computers. The human body, where is it in the human body?
Blood.
Blood is fluid flow, yes.
Nerves?
But specifically, nerves carry electrical current, okay? So no, but blood is a good example of this. Blood is absolutely the same thing, right? Blood is flowing through your body. There's a higher pressure that pumps the blood from your heart outward. I think aortas carry blood away, right? A away, wasn't that the whole idea in bio? It's all memorization. I always forget which one it was. But one of them carry it away and one of them bring it back to the heart to get oxygenated. Well, here, in this case, we can consider electric current, and we can see that the neurological? Is that like the brain and all your nerve endings, neurological? That system of your body is what carries electric current. So how come when you touch a burning stove, you're able to do this right away? Because the actual rate at which the signal is sent to your head is at the speed that electricity actually travels at, which is really just the speed of light, actually. We're going to see in this section that EM fields, electromagnetic fields, when established, travel at the speed of light. So we're talking about a ridiculous speed. That's why you can literally touch something that's hot and you pull your hand away instantly. Okay, what happens when people are on drugs? I know this is like the way they scare you when you're a kid, but it is true. It's not a joke, this kind of stuff. People are like tripping on like LSD and like stuff that's really bad.
Oh, that's what's yourself in there.
Yeah, all that stuff is off. There have been like stories, and these are not fake stories, of people like peeling their skin thinking that they're an orange. Yeah, like flaying layers of their own skin off, not feeling the pain. Terrible stuff. Yeah, people holding their hand on like hot stoves for a dare.
Nah, the dragon story is the best.
What is it?
The dragon story.
My friend told it's always your cousin's tripping on acid or something. He thinks there's a little dragon on your hand, and you stab your hand in the middle of it to get the dragon away.
Cut off your thumb.
Yeah, you cut off your thumb.
I've never heard that one.
No,
But this is true. Like the whole idea of like not being able to react.
Yeah, that's what happens in my eyes.
In Frank's eyes?
Yeah, that's what happened. I thought there was a dragon.
Your nervous system gets all out of whack. But the idea again is that there's actual electrical current flowing through your body. Now, when else could there be electrical current flowing through your body?
Getting electrocuted?
Exactly. That's when you don't want electrical current flowing through your body. Okay. So the term for current is actually the letter I. I'll leave it for you guys to figure out. Maybe one of you guys can research where that comes from. But the capital I refers to current. Q. What was Q from the last chapter? Little q was what?
Charge.
Charge. It's going to be the same thing, but we put capital Q here. It's really the same thing. I don't know why it's been adopted to be capital Q, but it's the amount of change in charge in a given time period. Okay, you see how it's a rate, electric flow rate really? Delta Q over delta T. Anything that's a function of time, right? What is velocity? It's displacement over time. It's a rate. What's acceleration? It's displacement over time squared. It's a rate. It's really just velocity over time. But these rates are things divided by time. So the current is the rate at which electric charges move. Okay, it's divided by T. This is the symbol for A. A lot of people have an abbreviation. What's the abbreviation for this word here that you hear all the time?
Amp.
Yeah, amps or amp, okay? You'll say, how many amps are flowing through the circuit? What that means is what is the current of the circuit? It's funny because, so I've worked with a lot of people that are like good with electricity, like electricians, but not many like electrical engineers in the past. I mean, I studied with electrical engineers, but like my uncle, one of my close friends, like a few of them are like really good electricians, but they're not certified electrical engineers. So the terminology is so funny because like I use the terms like current and stuff and say it'll be flowing, and they say, oh, what's the amperage? Not a real word actually. But the term makes sense because you think about amps, amperes is the term. So when you hear how many amps are flowing through the circuit or what is the amperage, somebody's talking about the current actually. Okay, the current in the system. And this affects, and we're going to see later in this section, how the current affects how much power you can generate from electricity. Okay, so if you have more current, you'll have more power. More current means more electrons flowing through, meaning that you could utilize the energy from those electrons or those charge carriers more, not more efficiently, but more of the energy you can utilize, generating more power. More power means you have like a brighter light bulb. Or, for example, the other day I was using a circular saw over there, and I plugged it into the wall, and I went to use it, and as soon as I turned it on, it was like, bzzz, and then the circuit, or the, whatever, it's probably a series circuit, a small one that's in a parallel, but that circuit was like overcharged, and it tripped the breaker, and it turned off automatically, because it was trying to draw too much current. So certain tools, and you'll know this if any of your parents ever used a snowblower? Any
Yeah.
parents have a snowblower before?
Yeah.
A snowblower, like a lawnmower, like a miter saw, if the lawnmower is actually usually gas, but some can be electric. But any of those big appliances need to run on their own line. So you see these air conditioners, they have their own line that's devoted to them. So there's a certain amount of current and a certain amount of voltage that goes to that line that can actually sustain the amount of energy that's needed to run it, the power. So certain circuits allow for more or less current to flow through them. If too much current flows through a circuit, that's what a circuit breaker is there for. It says, oh my gosh, this is too much for my circuit to handle. There's a rating on it. And what does it do? It flips a switch. And what does that do to the circuit?
Turns it off.
So what does it do
Opens
then?
it.
Opens the circuit. Literally, a circuit breaker. You ever hear that term before? Circuit breaker? The circuit breaker is like that panel you open up, there's all these switches, they look mysterious. You're like, oh, let's play with all of them? Don't just play with all of them? Usually you can just switch them all to one direction for off, one direction for on, they'll have a marking on them, and you try to label them in your house. So you know that, okay, you know what, there was too much current flowing through it, so the lights went out. You just go to your circuit breaker, turn it back on, but you make sure not to run all those appliances at once again. I've done it before where you have like a fridge running, and a vacuum cleaner, and a hair dryer all at the same time kind of thing. The circuit's going to go out automatically. It's drawing too much current, and it's unsafe. It can cause a fire. Okay, but that's the whole idea behind current, what it is.
Is that charge our phones and that's like,
No, honestly, it's a matter of just getting your stuff done before you come to school, preparing. Yeah, I mean, I don't really think it's about money because the money it would draw is not a lot. It really isn't. The energy that you take to charge an iPad or this is like nothing.
Yeah, I don't know.
You guys could do, everyone in school could do it all day and it wouldn't be money.
The only reason
It's more the entity, the idea of like coming to school prepared.
the only reason that
Seriously though, just so you know, it really doesn't cost money.
No, I know. The only reason that I think like a lot of us think that it has to do with money is because on orientation and refresher, Mr. Linus like specifically says the school has to pay for our bills and like we have to do
Maybe that's a
our-
way of saying it, but honestly, it's really preparation. And so, I mean, even myself, like when I go home at night, I charge my iPad like every night now, unfortunately. After having this for 3 years.
sacrifice for home.
Yeah, exactly. So, I mean, you have to do something though. Like I can't even see actually. But my iPad drains real quick now because the battery's getting weaker, so you have to do it. But it's just preparation. All right, let's take a look at this diagram and discuss what's happening. So this is a little bit confusing, so try to make sure you understand what I'm saying or ask if it doesn't make sense. We've talked about the electric field in a wire being described as the direction that a positive particle would move, correct? That's what we've been talking about the whole time. The direction a positive particle can move. So with electrons, or with circuits, what we're really looking at again is the direction a positive particle would move. So these are the electrons showing that they're moving to the left. So which way would a positive particle move then in the circuit? To the right. Okay, so the current is always opposite the direction of the electrons, or you could think of the current being analogous to the electric field. The electric field is in one direction, that's what gets the current moving in that direction. Okay? Let's see. You could have, well, all right, so you've seen this in chemistry before, it's just another idea, but this idea that, negative electrons are the thing that can flow, positive particles can flow, and you see these in physics like particle accelerators, but this idea of current is not just electrical current in a wire, but an example of something where you have both positive and negative flow to show this. Do you remember in chemistry, and you may or may not have done this last year, I don't know if you guys did, I think you guys have done like a potato before for like a battery and stuff to show that. And I think Mr. Joseph does one with like, what did you guys use? Pennies or something like that? Isn't there a penny one you did at one point? Okay. But there's also something where you can do this, and I don't know if you did it this year. You take salt and you dissolve it in a fluid, and it creates an electrolyte. You know what electrolytes are? Like
Yeah,
when you drink Gatorade, electrolytes?
We did the thing where we had to make our own batteries, which that was in use. Because, I use my own hands, and I like brass and copper, and there's and we put salt and like stuff to like make electric lights, and it like made the circuit increase.
Okay, so you've seen this before at least, the idea. Good. So the idea that I'm trying to get to though is that you can have negative or positive flow of particles. Don't just have that conception, because most students, when you're younger, what are you told? You're told that it's the electrons that move. And we've been talking about that ourselves with the charges, right? We've been saying, okay, if I rub my hair with a balloon, electrons are jumping from one thing to another, but there's no protons jumping from one thing to another. It's just the electrons moving because they're valence. They're on the outer shells, that whole concept, right? Well, the idea I want you to get at here, though, is that we're not going to look at the direction of negative flow. We're going to look at the direction of positive flow had it been, okay, for current. So let's look at a quick example. This section is really, really easy. There's only the one formula. When we get to the next two sections, we're going to see like 3 or 4 more formulas, actually. So we've got the startup current for a refrigerator. It's around 15 amps. But the running current is around 3 amps. We'll talk about that in a moment, too. For a 10-second time interval, how much more charge passes at a given point in the circuit during the startup mode than during running mode? So we've got 2 modes here, running mode and startup mode. So let's make a little, maybe like a little split. Okay, when it's starting up, the current is 15 amps. And once it's been running for a while, the current is 3 amps. Okay, you could say initial and final if you want, but I'm just making 2 scenarios. We know that 10 seconds have gone by in both cases. Again, this is why the math here is extremely easy. It's plug and chug, right? You've got your formula, I equals delta Q over delta T. In both cases, it's the same formula. And what am I trying to solve for? What am I trying to solve for? Yeah, the only variable that's not known, obviously, but clearly because it says how much more charge passes a given point. So we're looking for delta Q. Multiply those 2 together, we're going to get 150. What are my units for Q? Coulombs. And in the other case, the same formula applies. We're going to go ahead and say, all right, delta Q over here is going to equal the current over here, which is 3, times the time, which is 10. We got amps times seconds. Amps times seconds gives me coulombs. This is 30 coulombs. So what's happening here? We're going to explain the physical reason why there is more charge being used when you initially turn on the refrigerator. Why is there more charge being used when you turn on the actual refrigerator? What's the reasoning behind it? Better.
Isn't it that it takes up less energy? Like, so when it starts up, you need to change, the temperature, because the temperature inside is a much larger variant of the temperature that it needs to be at, so that once it makes it to that temperature, it takes a lot less energy to keep it constant at that cold temperature, because it's already that temperature.
Yeah, remember how we talked about mu? I'll let you guys to add on. Remember how mu static and mu kinetic? It takes a lot to get it going, but to keep it going, it's easy to move a couch kind of thing. The same, it's like analogous to what Benno had just said. Do you want to add, Katie? I saw you had a hand, sorry. Is that what you're going to say? Good, that's really good that you thought of that. Nobody ever thinks of that, but it's the same thing. Mu static is like starting up. So in a refrigerator, everything's warm. You got to get it down to cool down to that temperature. Now, another fun fact, completely fun fact that most people don't actually believe, but it is true. If your refrigerator ever goes out, you're better off not taking anything out at all, because the cold items in there are going to keep it cold. Now, in addition to that, stocking your fridge uses less energy too. Would you think would take more? Because initially everybody says, well, if you put like food in the fridge, it's got to cool off that food, so it's going to take energy to cool off that food. And that is true, initially. But once it's cold enough in there, and most of the occupied space is actually the items themselves, it takes a lot less electricity because it acts as like an ice block in itself.
Right. And it also, like, if you take, let's say like you take a piece of food or something and you keep that cold versus just like a contained amount of cold air, and then you expose that. It's a lot easier for the coldness to escape. So then probably as well, not just the stuff itself, but the how it's contained.
And that's the specific heat capacity you're talking about, really. When you think about it, right? You freeze something really cold and it has a certain specific heat capacity versus air, in which it could easily warm up very, with a simple draft of warm air rushing in to displace the cold air.
Right.
Okay? So that's the reasoning behind this idea here. Okay? All right, let's take a look at the next thing we're going to see. So for this next thing, I'm going to describe it. The concept first, I'll explain. So, drift velocity. Earlier I told you, okay, I turn on the light switch and it closes the circuit. So the electromagnetic field established is represented by the letter E there. Remember E right there? And this is the direction of the current. The current is going to the left. The charge carrier is moving to the right. Remember, the electric field is also the direction the current moves. The charge carrier is traveling to the right technically. Okay? Now, the charge carrier is in the middle of this metallic wire that has metallic atoms that cause bumps along the way. Imagine you're on a highway and you're literally bumping into everybody along the way. That's what's happening if you were running a marathon and it was packed. The very beginning of a marathon where everyone's there, that's what's happening here. This electron, or this charge carrier, I should use the right word, charge carrier, keeps bouncing off stuff. But the electric field itself travels at the speed of light. Again, the electric field itself travels at the speed of light, even though the charge carriers themselves are not. Those charge carriers, I have a number written down, I forget what it is yet. Charge carriers are the velocity of them when traveling through a circuit with some metallic wire. And it's not important to know the number, but just the significance. I mean, look how small of a number this is. I'll give you a description of what it really is. Ready? If I were to convert this to millimeters, it would be 10 to the negative 1. So it's 0.25 millimeters every second. How big is 0.25 millimeters? A millimeter is that tiny little increment. The smallest increment on a ruler is a millimeter. It's going a quarter of that every second. Now, it seems really slow, right? On a macro scale. It's not that slow on a micro scale when you think about it. Think about the size of an electron. That's like us running a quarter of a mile in a second almost. So although this speed is very little and very slow relative to things on a macro scale, it's actually not that slow when you think about the size of an electron moving. An electron is extremely small, and it's covering actually a pretty big distance for an electron, a quarter of a millimeter in a second. Okay, it'd be like us covering a mile in a second. You get what I'm saying? Okay, everything's relative here. But the actual velocity it travels at is slow. It's not the speed of light. But the field established is moving at the speed of light. That's why when you hit the switch, that light went on instantly. If this honestly traveled at such a slow speed, right, if it actually traveled at such a slow speed, it wouldn't actually be doing anything. It would take forever to get there, and then it would finally get there, and then it would start to, light up. Let me show you an animation so you can see this. And I did an example of this last year with marbles, but this is what the animation is going to show you. The marble one kind of worked, but I feel like students really understand it. And this one actually shows the actual electric field and everything. Okay. All right, so take a look at the board. What you're going to see, obviously, we have a switch here. When I turn the switch, what happens to the circuit?
Stops.
Yeah, it opens the circuit, literally, see how it's open? And now these charge carriers, what's happening? They're kind of just hanging out. They're really not moving. They're not able to be forced along. Okay, they're backing up a little bit at the other end of the battery, but they're going to stop. So I turn the switch back on, and I see it starts to move. The red arrow is indicating, unfortunately, I don't like this because of the direction it gives, but the arrow itself is indicating the speed of the electric field traveling through. See that arrow that's moving? Whereas the blue are considered like the charge carriers actually moving along. So what's happening is this. Every time there's a small collision between charge carriers, it's kind of like sending a message to the next one to get it moving. And then when it bumps into the next one, it says to continue to move. So they're pushing themselves along at a slow rate when the field itself is actually traveling through the circuit at a much greater rate. Okay, and I can change things, I think the switch, I can alter and stuff. I don't think it was actually worth it. What did this do? No, this just opened and closed, and that's what it was. Yeah. Okay, so this is the concept here. That red, see that red light right there? That's showing that, or the red arrow, that just turned the colors. That's showing the electric field itself traveling through the circuit at a given speed. Take a look at the light bulb, ready? So when it gets to it, it turns on. You see that just turn on there? That's establishing, and this is, you guys, this is in slow motion. This is not real time here. Okay, but this idea is that right now, the chandelier is off. But as soon as I turn it on, it establishes a field. That field is what physically moves. The field is moving fast, and that gets the light bulbs to actually turn on. And then those charge carriers, one at a time, are giving that light bulb more energy. We'll talk about this with circuitry, but they go back to the battery, they get charged back up, they go back to the circuit, the energy gets used by the lamp. They go back to the battery, etc., over and over again. Okay? A circuit is, as you know, cyclical, right? It continues over and over again. So that's the idea here behind drift velocity. I want to go this section on this. We're going to talk about two sources of current that are the two most common sources of current that occur. First, batteries and frames. Is this what you're talking about, by the way? Something like this? Did you guys build a salt bridge ever or no? Did you do it with your fingers, you're saying?
No, we had about do our own
We
batteries.
did this exact thing in class.
Yeah.
Oh, you did this in class?
Yeah.
Okay.
But we
Did
had
it
a
work well, or
project.
how did it work?
Yeah. No, I think it screwed up. It didn't really work. But
It's hard to generate a lot of electricity. That's why. You know
Yeah.
what I got to give him? I have LEDs that take very little energy. Did you use LEDs or actual bulbs?
actually, what was I saying?
I'll give him just LEDs because this is enough energy to power an LED for sure.
Yeah, no.
Might do a
what-
better job showing the light.
What Frank was talking about was like each one of us made our own batteries. So
Yeah,
like,
I heard
So
about
like
that.
we made one like where we had like a tray of ice cubes, and we would take like we took these zinc bolts.
Yep.
And we did that.
And they went from one to the next.
Yeah,
And
and
it
it like generated a lot of energy.
I've seen videos of that. It's pretty cool. But yeah, that's the first idea of a battery. And a battery, what does it do? It's a conversion of chemical to electrical. That's the important part about a battery. It converts chemical energy to electrical energy. That's what a battery physically does. That's why you learn about batteries in chemistry. Chemical energy. If you're into chemistry, honestly, and you really like physics too, or science, chemical engineering is a field that's huge, especially nowadays. Everything is electrical and chemical now, more than mechanical. Mechanical engineers 20 years ago and civil engineers were like the only real engineers. Electrical engineers and computer engineers didn't really exist that much until like the 60s and 50s when they like started having computers and stuff. But back in the day, and you can learn about this if you read about engineering, even chemical engineers, they weren't engineers. Honestly, they were mainly like doctors and like pharmacists at the time. And a pharmacist kind of was like a chemical engineer. They would learn how to put like what they called potion at the time, or like things like that, meaning like herbs and stuff to help your body with chemicals. And a lot of the time that happened, they didn't always succeed. Whereas now with chemical engineering, we learn how to really optimize things and make them work for us, for our needs. So this is converting chemical energy. Now, generators are where mechanical engineers really were started. You take something that can turn another thing, it generates energy, hence the term generator. If your power's ever gone out and you have a generator at home, you know that you need a hand crank. And usually you pull on the hand crank to get it started. Or your generator that is powered by gas might have a little electrical battery on it. And the battery is what gets it started maybe. But a lot of old school generators, you would pull on it like a lawnmower. That's what a lawnmower is doing when you're starting it up. You're starting at the cycle. And what's happening here really is that you're rotating a wire through a magnetic field. And we'll talk about magnetic fields, that's in chapter 20. Or 21 actually. Magnetic fields are what induce currents. And when you rotate this through a magnetic field, it causes a current to actually flow on its own. But it's taking your mechanical energy and converting it to electrical energy. Okay, mechanical energy to electrical energy. What other type of energy nowadays do we really try to push to convert to electrical energy?
Solar.
Solar, or what general term for that?
Wind. Oh,
General term for all that.
alternative.
Alternative, or there's another one. Natural, eco-friendly. The term I use because it makes sense because of what it is. Renewable. Renewable because why?
The sun keeps coming.
Yeah, you don't run out of it. You're not going to. You will eventually one day, millions of years from now, whenever the sun explodes, we all die. Well, not we, but somebody does. But the idea again of renewable energy into electrical energy is probably the most prominent thing right now. So if you consider studying like science as a field, or you're really into that kind of stuff, and you want to think about that, that would be like your environmental engineering. And usually civil and environmental engineers start together, and then they branch off after that later in their career. Okay, so these are the two types that we're going to look at, the two types. And we're going to see an example of a generator in a moment, but before I get to these types of current, because the generator is going to show current in a second. So there's two types of current. You learned or you've heard of AC/DC, the band. You know, AC/DC is alternating current, direct current. It's not for that, obviously, but AC/DC, alternating and direct. AC current, alternating, it does exactly what it sounds like. It alternates. It goes back and forth. So you're going to see with the direct current, the actual current measured is always a positive value. Because the current, when it's direct, is always doing this. Okay, it's always flowing in one direction. When we do a lab later in the year, we're going to do a little circuitry, and I'm going to have to use a battery. And the battery has a positive end and a negative end. And the electric field can only flow from one direction to the other. So when you make your own circuit later in the year, it's going to be a direct current. Okay? Most things, though, run on alternating current. Okay, and most things, and I mean most things in like first and second world countries. A lot of third world countries, though, will still use direct current, okay, which is not very safe.
That's the
actually.
first current, right?
Correct. Direct current was first discovered. Now,
Nicholas
alternate,
tells us.
yes, it was
Oh,
definitely.
I remember that.
Alternating current, the idea behind it is that the end of the battery or the end of the source of energy is rotating, switching. And the easiest way to see this is actually with a generator. If you have a generator where a magnet is spinning and that magnet end keeps switching, positive, so there's a north end and a south end. As the magnet switches ends and it keeps rotating, what does it do? It causes an electric field in the actual coils, in the wires. And that field goes one way, and then it goes the other way. And then it goes one way, and then it goes the other way. And it keeps going back and forth over the battery, allowing the carriers to actually generate back power. So let me show you a little demo of this so you can see it. That's what I was talking about the other day, guys. So some of this stuff, especially in this section, you're going to notice is much better to see with some sort of a simulation because you can't physically see a lot of this stuff. So let's take a look at this one here. So look what's happening. First, we've got water flowing out of this spigot. If I turn off the water, it's going to stop this thing from rotating. So here's some renewable energy, gravity. Gravity is a great form of renewable energy. If you could generate so much energy off of water, it'd be great because water is always flowing because of gravity. So you put like a little sort of a windmill or like a water turning device in a stream. The stream turns the device spins an axle. The end of the axle spins a magnet. The magnet is next to some coiled wire. The magnet spinning induces a current. Induces means causes a current. The current in the wire starts to generate. If the poles of the magnet keep switching, the current goes one way, and then the current goes the other way. It changes the direction of the current. So as soon as I turn this water on, even very lightly, look what happens. You're very lightly, the smallest stream possible. This is moving. Look at the current here. So it's all moving in one direction, right? And then watch, ready? It's going to stop, and now it's all moving back this way. Do you see that? Because now the North Pole is leaving it. So now it's going to be moving clockwise, or if you will, like this, in this direction. I'm looking at the electrons right here, the charge carriers. Once the South Pole passes it, it's going to start to move down again. South Pole passes, it stops. And then it starts to move down again. What can I do? I can speed this up so you can see a little bit better. Okay? Look at the current. The current is literally going one way then the other, one way then the other. That's what an alternating current actually looks like. You can't see it. It's impossible to show you this with a circuit, like when you're physically seeing it. But this actual current is fluctuating back and forth, back and forth. Now,
Can we go to the highest?
our current goes at such a high frequency that we don't see flickering of light bulbs, but bulbs actually flicker.
Oh, because
Isn't that crazy?
when you take a video, sometimes.
If you go slow-mo enough, you can see the lights kind of like flickering like that. Absolutely. Okay, here's the fastest it allows me to go. Okay? But if you think about it, can you really, I mean, I know right now you can see the flickering, but for the most part, it would be pretty bright in general. But this is not even a fast speed. It goes a lot faster. The current goes so much faster than this, so you literally don't see lights flickering. It's not visible to the naked eye. Okay, but with a super slow-mo cam, you can actually see it. All right. I think that was the last thing I wanted to go over. Let me see.
Yeah, that brings me.
Next thing's homework, right? All right. So that's really it, guys. So this was a high section. The math part was I equals delta Q over delta T. That's kind of it. All right, so don't really focus too much on the math of this section. Focus on the theory. And then in the next two sections, when we start to look more into electricity and power and voltage, you're going to see a lot more math occurring there. Okay, let's